Okay, welcome back everyone to indeed the final day of mini courses. Raymond will give his final lecture on Causal Homology.
Thank you. All right, so I want to recall this diagram, which we got by looking at an associated graded to our full complex. And this is just a schematic of what was going on. We had some sections of the ring of functions, holomorphic functions on several copies of our elliptic curve. So these are functions in 2 copies, these are functions in 1 copy, and these are just functions in 0 copy of the elliptic curve. We allow some singularities here. We are allowing singularities at 1 point. Here we're allowing singularities at the diagonal in the surface and, well, at the 2 divisors that you get by looking at the point times your curve. And since we're able to trade in our complex derivatives of functions by the translation operator acting on the corresponding factor of the vertex algebra, then I get to look at a basis for these spaces of functions. So this derivative functions modulo total derivatives on this affine space, which is several copies of the curve minus a divisor, that's the top, the middle, the RAM homology, which happens to be the top, the RAM homology of that curve. So I get to choose a basis for that, and here is some basis, the constant function, which I'm putting here because remember in the filtration, I was counting number of poles. Then I have the Weierstrass P function or this zeta function. So that's a schematic to saying, well, I'm looking at x squared minus this diagonal divisor, which is just x is equal to y, or the point x is equal to 0, or the divisor y is equal to 0. And when I write p, I could mean p of x, or p of y, or p of x minus y. And these guys are not linearly independent in the RAM homology. I can trade one by the other one by taking derivatives of another function. Here, when I write z, this was this function. There was z of x, y. There is a new function that happens in this square of this guy, which was the Weierstrass zeta function of x minus y minus z of x plus z of y. And the derivatives of this are linear combinations of this. So those are these 2 functions. And here I'm taking product of those kind of functions. But the whole point is that when I take the differential in the complex, that was sort of like a Lie algebra differential, then what can happen, I cannot go down. Namely, I am not going to remove 2 poles. So this kind of things is not happening, and this is because of my filtration. So later today, with any luck, we're going to analyze what happens if I don't look at the filter, the associated grade. But I've passed to my associated grade with respect to both the filtration by poles on functions and an increase in Lie filtration on the vertex algebra, and that's why I got this Poisson vertex algebra. So now we were looking at this complex here that I see in the top row. Namely, I am looking at what happens at the top part of the Hodge filtration and several copies of my associated graded to my vertex algebra, which is a Poisson vertex algebra, and analyzing this differential. Okay, and so I stated a theorem last time, and Anne requested details on that theorem, so let me write it again, and let's prove it. So first of all, let A be a graded. So this is a graded differential commutative associative algebra. So it has a derivation of degree 1. And let's suppose that it's generated as a differential algebra by A0. we will also need that this A0 is of finite type. So the arc algebra of a finite type affine scheme would be such an example, okay? Or any quotient of those. So now, whenever you have an algebra with a derivation, there arises a Causal complex, which has A in degree 0. I'm going to put omega 1 of A in degree 1. I'm going to put wedge 2 of omega 1 of A. This is the wedge product over A, and so forth in each degree. So this is the de Rham complex, well, the de Rham algebra of A. This is just the modulo of Kähler differentials. And the differential in this complex is given by contraction with your derivation. So the differential here goes to A TB, and the differential here, A dB wedge dc, goes to A TB dc minus A TC dB, and so forth. So you view your derivation by the universal property of Kähler differentials is a morphism of A modules from omega 1 to A. And this guy is a free commutative algebra generated by omega 1 of A. Extend T by the Leibniz rule to a derivation of that free commutative algebra, okay, of degree minus 1. So this is a complex, and the homology of this complex I'll call the Causal homology. This is a Causal complex. So I'll call this complex K dot of A, and I'll call its homology HK dot of A will be the homology of this complex. So this is a Causal homology. So we immediately see something. We see immediately that HK0 of A, well, is all of A modulo the ideal generated by derivatives. Since my differential algebra as a differential algebra is generated in degree 0 by A0, this thing is A0. Okay, so A modulo everything that takes a derivative is just A0. And what I stated last time is the following: is under these conditions, the theorem, is that the first degree homology of A is 0 if and only if A is freely generated by A0. A is the jet algebra of A0, of its degree 0 part. So arc spaces have vanishing of the Causal homology, and any space that, and conversely, if you're not an arc space, then your Causal homology is non-zero. So let's prove this statement. Okay, so we'll start with, proof. We'll start with the case where A naught is a polynomial algebra. So it has to be a finite type algebra, so I'm going to take an affine space of finite dimension. Okay? So in this case, this Causal complex is really a Causal complex. So in this case, this K is an actual, is a Causal complex. Associated to a regular sequence. Well, what am I proving? So I'm taking A naught to be that. I'm going to consider A to be the arc algebra of A naught, and I want to prove that its Causal homology is 0. Okay? So I'm going to be proving this situation first. In the case where A is the arc space of just affine space. So in that case, this A itself is a non-Noetherian algebra. Anne explained this, that this is generated by this. It's a polynomial in infinitely many generators. Here I goes from 1 up to K, and j is bigger or equal than 0, I can consider this j as the number of derivatives that I'm taking of each one of the generators. And, well, so this, in this particular case, this causal complex that I'm writing here is the causal complex associated to a regular sequence that is going to be, not strictly speaking, a regular sequence because I'm going to take an infinite number of generators. And to give you a regular sequence in a ring, I need to give you an order set of elements of that ring. So the order set that I'm going to pick is going to be a completely ordered, a complete order on the set of generators here, where I'm going to declare that xij is less than xkl. Well, if so. I'm going to declare that if j is less than L, then this guy is smaller than this. And if they are equal, then I'm going to look at I less than k. So that's a lexicographic order in the generators. And that gives me a complete order. And with respect to this sequence, which is an infinite sequence, if you write what the causal complex would be, then you would get this diagram by replacing the differential of, say, xij by xij minus 1. So you get this sequence, you plug this sequence in this causal machinery, and it's going to give you a complex that is isomorphic to that. The only problem is that we cannot state that this guy has vanishing homology, because the theorem is that if you have a ring, and a regular sequence in that ring, namely finitely many elements that satisfy the usual properties of not being zero divisors and the quotients by them not being zero divisors, not having zero divisors, then the causal homology vanishes. But I'm taking an infinite sequence. But now I can do the trick that Anne did, and I can look at the subalgebra of A generated by the xij for j less or equal than a fixed number, n. So these are some algebras of jet spaces instead of arc spaces. And, well, I wanted to check that this homology would be 0 for this whole ring A. So if I take something in the kernel of this differential, I want to prove that it's in the image of the differential. If I take something in the kernel of this differential, then it's built out of linear combinations of products of these generators, and I look at what is the smallest n such that my element is there. Probably plus 1. So now, well, no, just that n. So now what happens is that the vanishing of the causal homology for this algebra would imply it for the bigger one. Because anything, I take my element, I apply the differential, it goes to 0. By the vanishing of the causal homology for usual regular sequence, I will find out something in the preimage where I replace A by the subalgebra generated by those guys, and that's still something in the preimage for A. So that proves that the arc space of affine space has vanishing causal homology, because the arc space of the jet algebra has vanishing causal homology. Okay, so now, what happens if I take a subvariety in that space? So I want to mod out by some ideals in the affine space. So for now, suppose that A0, that if you take the arc space of A0 and has vanishing causal homologies. So HK1 of J infinity of A0 is equal to 0. Let's suppose that we have such an algebra. For example, when A0 is polynomial algebras in K elements, we've already proven that. So now let's pick an element, a non-zero divisor in A0. And I want to prove that the arc space of A0 divided by the ideal generated by F also has that property. Vanishing HK1. If I prove that, then since any algebra of finite type, I can build it starting from some affine space by taking quotients, then I prove this theorem, I prove this direction of the theorem. So I need to prove this. All right, so, well, we have a covering of our A0 to A0 divided by F. Therefore, I have a covering of the arc spaces of A0 to the arc space of A0 divided by F. So, okay, so I want to grab something in the kernel omega 1 of A0 divided by F that is in the kernel of the differentials. I want to grab something here, and I want to prove that it is in the image of the differential here. So I want to look at something here. So I'm going to grab some form in A1, in omega 1. So this is the sum of something, I don't know, AI, D of BI. Let's put bars on these guys, where each one of these guys is in, oops, this is the arc space, and this is the arc space. So each one of these guys is in the arc space of this algebra, okay? And I assume that the differential of this is 0. Okay, we can lift this to the whole algebra A. So pick representatives of these guys in A. I can probably remove this statement of theorem. So pick representatives of these AIs and BIs. So these are in the algebra of A, of A naught, not of A naught divided by F. And let's take D. So then D omega, well, this guy is not 0, but it is 0 once I pass to B. Well, once I pass to this arc algebra. I was calling, in our paper, we call this guy B. So this guy is non-zero, but it is a combination like this. It's some Cj, probably I'm going to use Ck, and then some derivatives, K's, of F. Remember that Anne proved that the arc space of A0 divided by F, the arc space of A0 divided by F was a quotient of the arc space of A0 divided by the ideal that is generated by F. Oh, I think I'm using T instead of that. T of F, T square of F, and so forth. Okay, so here I need to use T, not del. I think I'm going to make this mistake all the time. So when I take the differential, then it should be in the ideal that I'm killing when I pass to this arc space of this quotient. So it is a combination of guys like this. No. So this is, no, this was just to identify the regular sequence with the random difference. The differential sends dx to tx. So that's the differential in general. Just, you have a dx, just put a t instead of a d and contract that. So, okay, so now we realize something. So if I look at these guys, then the first thing to notice is that this guy cannot be of degree 0. Because if I had something in degree 0, well, we've already checked for A0, well, that we didn't have. So we've already assumed that this guy is generated by its degree 0 piece. So let's take something here of degree j. Let's take omega of degree j. Okay. So now these guys, the t is of degree 1. So this guy here f was in degree 0, this guy has degree k, therefore ck has degree j minus k. Here, k goes from 0 up to j, I suppose. The degree of omega that I took was j. Okay, so what I realized that we can integrate this. We can integrate ck t to the k f is d of ck t to the k minus 1 d of t to the k minus 1 f if k is bigger or equal than 1. I can integrate it. So whenever I see a d, I put a t. So the differential of this thing is the Causal differential of this is replacing this d by a t, which gives me this tk minus 1. Which this gives me tk minus 1 times t, which is t to the k of f, which is this. So now the problem is that I cannot integrate the guy when k is equal to 0, right? Because I cannot find this t to the k to t to the minus 1 of k. But anyways, I can just grab my omega and I can subtract that thing. I can subtract the sum when k is bigger or equal than 1 up to j of ck, well, this, the differential of t to the k minus 1 of f. And now this is in omega 1 of A, omega 1 of the jet algebra of A naught. And the differential of this thing, well, is the differential of omega minus all of this sum, but still the k equal to 0 part survives. So the differential of this is C naught times t to the k of f. Well, t to the 0 of f, which is C naught times f, which goes to 0 when I mod out by f. Okay, so now we realize that since C naught, so f is in degree 0. I'm modding out something in A naught. But the degree of C naught was j, which is bigger than 0. So since the degree of C naught is equal to j, which is bigger than 0, then there should be a derivative in C naught. So this C naught is going to be written something like a linear combination of guys like this for some A and B of appropriate degrees. I mean, the point is that the degrees of these two, oh, again, I need t's. The thing is of degree bigger than 0, so therefore at least one derivative should appear. So actually the degree of A and the degree of B should be, the sum of these two degrees should be j minus 1, so that with t you get the degree j that you want, which is bigger than 0. So therefore this guy is also in the image of the differential, because we can grab f, we can grab A, and we can grab dB, and apply the differential in the Causal complex to that guy. And this is just f A dB, which is C naught f. So then if we grab omega and we take the sum of ck d, this is k bigger or equal than 1, dt k minus 1 of f. And then now we subtract this f A dB, or linear combinations of these such that C naught is equal to that, then the Causal differential of that is 0. But now this is a 2 form in A, well, in the arc algebra of A naught, and you can just take the image of that guy. So take the image of this guy in omega 2 of the arc algebra of A naught divided by f. And the differential of that guy is going to be your omega that you want. I think the same argument works. I don't remember if we checked this, but I think the same argument produces classes. But in general, you have this theorem that for nice rings, and these are all nice rings, if you have something that is K1 regular, then it is K regular. So I suppose that that abstract nonsense works in this situation, and just all the higher homologies are there. And there's some subtleties of having non-Noetherian rings, but I suspect that this is completely relevant here. Okay, so we've proven that the arc space of an algebra has vanishing Causal homology. But we need to prove the other way around. And the other way around is very simple because, so now I want to grab an algebra that is not an arc space, and I want to prove that its Causal homology does not vanish. So let's take the arc algebra of A that covers, of A naught that covers A. My A is generated by A naught, so if I take the arc algebra of A naught, by definition, I have a surjection like this, and I get an ideal, and this is a differential ideal. So now what I notice is that we never used, so to talk about Causal sequences, you'd never need a unit in your ring. Causal sequence works. The differential is well defined whenever you have a ring. So just take the same definition for I, which is not a ring, but it has a multiplication, it has a derivation, it's closed under differential, the differential is of degree 1. It works everything the same except that it is not a unital ring. But you have the same complex, and the complex that computes Causal homology is a functorial complex. So you get a long exact sequence from HK0 A to 0 HK0 of the arc algebra of A naught, HK0 of I, HK1, which is what we want to compute, of A, and well, let's continue from here, HK1 of the arc algebra of A naught. So what do we know so far? We know that this thing here is A naught. This thing here is also A naught. Both algebras are generated by the same A naught. This is surjective, therefore this is an isomorphism. Therefore, whatever this is goes to 0 here. Okay? Whatever this HK naught of I is, it goes to 0 here. This guy is what I want to compute. And since this map is 0, this map here is surjective. And actually, this is 0 because it's the arc space of something. So this is 0. That means that these two guys are isomorphic. So if I want to prove that this is non-zero, I need to prove that this is non-zero. And HK naught of I, again, is by definition is I divided by these elements in I that are the product of some T in I times something else. So namely, this guy here, by the same argument that we proved that HK naught of A is A naught, this thing here is the quotient of I divided by guys of that form. That was the differential in I. But now I is an ideal that is generated in degree bigger than 0. It's explicitly generated in degree bigger than 0 because, well, I assumed that this algebra was generated by A naught as a differential algebra. So the degree 0 piece of this algebra is equal to the degree 0 piece of this algebra. So this ideal here has no elements in degree 0. That means that all of these guys are bigger than the smallest degree in I. So if you take the subspace of I that has the smallest possible degree, which is bigger than 0, can never contain elements of this form. So that means that this space is non-zero. Therefore, this space is non-zero. Okay. Okay, so that proves the vanishing of Causal homology for arc spaces and the non-vanishing for non-arc spaces. So we get some vanishing. So now I want to continue with our analysis of why this was interesting for, yes?
I believe the diagram chases diagram in this case, but are you also saying that
I'm not sure I follow the question.
I mean, you didn't say it, but from the way you wrote this long exact sequence associated to a short exact sequence.
Oh, I just have these complexes. So I have a short exact sequence of complexes. And I just take homologies. Homology is a delta functor. So if you have a short exact sequence of complexes, you take homologies of the complexes and you get a long exact sequence on homologies. So there's no need for these functors to be derived of anything. Okay. All right. So now, so I want to get back to why this was useful for us in chiral homology. And this came in the analysis of this complex here. Recall that this is the easy part of our complex, is that computing these differentials is very simple when I took the associated graded, because I only care about the singular part of these functions. So here, for example, I looked at the function p, that in our language, this was just 1 over t squared, because anything that is regular is going to disappear in the associated graded. So that differential is of that form. So this is p of t. And when you map it to that guy, you just get a minus 2b when you map it to a. So the degree 0 homology of this complex, of the top row here, is just a divided by the minus 2 product from a tensor a. So you just get a0. So let's call our complex, I think last time I called it K, is the complex that I get, is the top row of the chiral homology complex, of the associated graded to the chiral homology complex that we wrote. So that's this guy, has p's and p zetas, and then 3 copies of A, and then it maps to just p and 2 copies of A, and then it maps to the function 1 and just 1 copy of A. And the homology in degree 0 of this complex, no, this is a different than HK. So the homology in degree 0 of this complex is A divided by ATA, which is RV. Remember that A was the associated graded to respect to the leaf filtration of the vertex algebra V. So if I divide by derivatives, I just get RV. So in degree 0 of this complex, I find RV. What about in degree 1 of that complex? Well, I need to analyze what is the differential of these 2 guys here. And what I recognize is that this differential here and this differential here will combine to give me the Causal complex of this guy A. So that's why this appeared in an interesting fashion. So yeah, so let's work that out. So if I look at the differential of this function p times p, so this is in the associated graded to chiral, well, this is in the Causal, in this K complex of this p times p of A tensor B, tensor C. Let's do this one first, times the zeta function. And here I'm going to use that this, if you remember the zeta function x, y, was just simply z of x minus y minus z of x plus z of y. So the singularities of this function, they really simply look like x minus y. That's the only part that is going to contribute for my differential. 1 over x, 1 over y. And I see immediately how these singular functions are going to contribute. When I look at this singular guy, I'm going to have a product of A times B. The minus 1 product, because it's a pole of order 1. So what I'm going to see is that this function is going to remain. That's the P that I see there. That's the pole that I maintain. But then I'm going to have A times B, the minus 1 product. That is just the product in the algebra A, in the associated gradient. Tensor C. this function here is going to put is singular only when x is equal to 0, which means a gets multiplied by c. And this other function is only singular when y is equal to 0, which means b is multiplied by c. And this is the Hochschild differential from a tensor A to a. Oh, sorry. From a tensor A to a tensor A. So since this is a Hochschild differential, I can kill the image of this differential, and I pass through a quotient where I had a tensor A. Again, this is just the component that has the function p. There's another component when I take the function 1, or gr minus 1 in the Hodge filtration for functions. But then I look at this modulo the image of that differential, and I find omega 1 of A. So now I have omega 1 of A mapping to A, and the differential here stays the same. Under A tensor A, the map to omega 1 of A that sends A tensor B to ADB, this differential stays being ATB, just like in the Koszul complex. But now I haven't taken omega 2, but I have this A, and I still have the remaining function, which is P times P. And when I take the differential of this function, which I need to analyze, I'm going too slow. So when I take the differential of the function P times A tensor B tensor C, well, let's look at what this is. And then again, I'm going to take P of x, for example, times P of y. And this is singular only at 1 over x squared times 1 y squared. Oops. Yeah, that's correct. So this is 1 over x squared. These are the singularities. But the point is that if I look at the singularity at x is equal to 0, I keep my 1 over y squared, which is the p function that is going to survive, and I'm taking t of a times c. So this is the p function that survives because of the 1 over y squared, and then I take a t of a times c. And then when I look at the singularity at y is equal to 0, I pick up a b times c. Oh. I pick up a t of p times c, because it's 1 over y squared. This is a minus 2 product of b with c, which is this product. And then I keep my a, and I keep my pole, the Weierstrass p function, because I still have this 1 over x squared here. So that's as explicit as that. And then you see that this should be killed in this omega 1 of a. But precisely that is the image of the Koszul differential from omega 2. So if I look at omega 2 of a, and I map here, that thing there is the image of the Koszul differential. In other words, there's a quotient map like this, and this differential here factors through this map. So the homology of what I find is that the homology of this complex coincides with the Koszul homology of A in degrees 0 and 1. And I don't know how it continues. And I actually don't know how it continues. But in degrees 0 and 1, it is exactly, so the homology of the complex K, that is the top row, is equal to HKN of A if n is 0 or 1. So in particular, this is going to be 0 if our algebra is an arc space, which is the definition of the vertex algebra being classically free. Okay, so we found something that is involved in chiral homology. We have our complex K that is a subcomplex of the full thing, of the associated graded to the complex that computes chiral homology. And let's define the quotient to be P. So this is the definition of P. I'm going to take the quotient by this thing, and in these degrees, I see this part that I need to analyze. Okay. Okay, so let's analyze that part. Okay. Well, so the first thing I notice is that this P will not have homology in degree 0. Okay, so I need to analyze, want to analyze the homology of this complex P dot. Okay, so what I have in degree -1, which is the only, well, I'm sorry, in degree 1 is the only thing that survives, is this guy here. And I have the function 1 times A tensor A. This guy maps to 0. There's nothing in this complex in degree 0. But then I can look at modulo the images of these guys and see what I get. Okay, so the first thing I notice is that if I look at modulo the image of functions P's, so again, I have A tensor A tensor A, and I need to look at the images of the differentials. So I can look at elements like this form, P of X, A tensor B tensor C. And again, since I only care about the singular part of these functions, this goes to, this is 1 over x squared, so this only has vanishing, has a pole at x is equal to 0, so this goes to B tensor TA C. And if I look at P of y, A tensor B tensor C, then this goes to A tensor TB C. And if I look at P of x minus y, A tensor B tensor C, then this goes to TA B tensor C. So all of these things vanish in the homology of that complex. So I can quotient by everything that is in the image of this P part of this complex. So when I quotient by that, so if I look at A tensor A, modulo the differentials of functions that are of the form P tensor A tensor B tensor C, I find the quotient of RV times tensor RV. So I get the quotient of RV tensor RV. Okay, so this came from analyzing the quotient by the P functions here. But I still have a couple of differentials. I have this zeta function that goes to something here, and I have the 1 function that goes to something there. So by the same argument, if you look at the zeta function, you're going to get the image of the Hochschild differential. So take A tensor B tensor C. Again, the zeta function looks like I did here. You get these 3 alternating sums of the different products. So when you take the differential of this, you're going to find the image of the Hochschild differential, but now for this commutative algebra. So you get Hochschild differential for RV. So when you kill the differentials of this, so you pass through that quotient, and you get omega 1 of RV. So what we found so far is that the homology of the complex P in degree 1 is a quotient of omega 1 of RV. Where I need to tell you what is the differential there. And that differential is the only remaining differential that comes from here, from taking 1 to this 1. So what is that? Well, I look at 1 tensor A tensor B tensor C, and I need to apply the differential of that thing, and now it was a residue. So the only thing I need to take is the 0th product. So I get A 0B tensor C. When this thing is regular, so I only get the residues when I apply each one of them. This time I do care about the regular part because I'm going up in the differential. I'm not going in the same degree. Okay, so this gives you this minus, modulo perhaps a sign, but it looks like this. Plus B tensor A0C. So let me tell you exactly what happened here, that this is something that is mapping from A tensor A tensor A, but it's going to factor through omega 2 of RV. So I have this omega 1 of RV that was the quotient, and this is, I'm describing to you a map. It's exactly the same situation that happened for A. We have this map from A tensor A to omega 1 of RV that sends A tensor B tensor C to this differential, and I claim that that factors through omega 2 of RV, where here I put the Poisson homology differential. So this is where a different homology appears. So let me tell you what that is. We've already seen the Poisson homology. Now I can remove this piece. No, probably. I'll keep it. So we've already seen the Poisson homology appearing in the first lecture because the zeroth Poisson homology was the classical limit of chiral homology in degree 0. But now we're seeing the first Poisson homology. So if you have a Poisson algebra, it's a Poisson algebra. Then again, you take the de Rham complex of that algebra, well, the de Rham algebra of that algebra. We only care about this part, but this continues. And this acquires a differential that now will depend on the Poisson bracket. So the differential is A dB maps to the Poisson bracket of A and B. And if you give me A dB dC, this maps here to, well, the Poisson bracket of A and B dC minus the Poisson bracket of A and C. Again, the signs I might be getting wrong, dB. And then there's one extra guy, which is I take the Poisson bracket of B and C and take D of that. And this extends to the whole the Rham algebra of RV. And the homology of this complex is called the Poisson homology. So I'm going to call this complex P of RV. And the homology, I'm going to denote it by HP dot of RV. It's called the Poisson homology of RV. Okay, so now, this differential here looks exactly like this differential here because the zeroth product in A, remember, the zeroth product in RV is the Poisson bracket of A with B in RV. So this thing here looks exactly like that when I realize that I'm identifying these guys. This is in A tensor A. But I've already looked at the quotient by the P functions, and I moved to omega 1 of RV. So the map from RV tensor RV to omega 1 of RV sends this, tensors this, to this guy, DC. So this goes to the Poisson bracket of A and B, DC, which is this term here. And the other two terms are the same. Okay, so let's summarize what we've gotten from our complex. I have a short exact sequence that is the conjugate, the top row, mapping to the full associated gradient of the Rham guy. And the quotient, I'm going to call, P is a bad idea because I've just called P the Poisson guy. Well, let me call the quotient Q for quotient. So I have this quotient like this, and I have a long exact sequence in homology there. So what is this long exact sequence in homology? Well, I'm going to get H0 of this Q to 0. But this we know already is 0, because there's nothing in degree 0 in that quotient, Q. We get H0 of the associated gradient to chiral homology. And we've already computed this guy. this is RV divided by Poisson brackets. And by the description I just told you, RV divided by Poisson brackets, this is HP0 of RV. So that's what we get in degree 0. HP0 of RV. So now I look at H0 here. But this is the 0th Causal homology for A, and therefore this is A. Oh, I'm sorry, A0. Right? The Causal homology in degree 0 was always A divided by derivatives. So, okay, fine. This map is surjective. It's true. The map from here to here is just take Poisson brackets. So the differential here is just taking Poisson brackets. Okay, so the kernel of this map is surjective because this guy was 0. And the kernel of this map, of this delta, is equal to the Poisson bracket of A0 with A0, which is of RV with RV. The derived algebra of RV. That's the kernel of that map. So let's continue with the long exact sequence. I have an H1 now. Well, let me write this in a different board. Probably here. So the long exact sequence in homology will continue with some, let me write this H0, K dot. And this receives a map from H1 of the quotient. And we've already identified this. Then this gives me an H1 of GER of the chiral. This is what we want to compute. We want to compute the first chiral homology. And this receives a map from H1 of K dot. And this, we have some control of if the algebra is classically free. For example, this is 0. Okay? Okay, so the first thing to notice is that this guy here was a quotient of omega 1 of RV, where I killed out the differential of the Poisson homology. So I only need to analyze what is this connecting homomorphism between H1 of Q to H0 of K. So this is the only differential that we haven't analyzed, which is this one. This is the only differential that goes from this complex from degree 1 to that first row, top row, in degree 0. And this differential is very simple to describe. This is the function 1 that I have here. So here I see 1 tensor A, tensor B, that goes to the Poisson bracket of A and B, because it's the 0th product of A and B. So this map here is the Poisson. This map delta is that map. Is the map that sends ADB to AB. That means that if I look at the kernel of this map, I find the kernel of delta is exactly, would give me this Poisson homology, HP1 of RV. Okay, so this analysis was kind of slow and long, but we've managed to prove the following theorem. So the theorem is that if HP1 of RV is finite dimensional and the dimension of HK1 of GERV, so this is A, the Poisson vertex algebra, is finite dimensional, then chiral homology is finite dimensional. Of H chiral 1 of V is finite dimensional. Okay, so I've bound this complex by this group and this group. This one we have some control. If for example, every C2 cofinite algebra would have this guy being finite dimensional. and even less, so every, well, I'm not aware of nice examples of algebras where this is finite dimensional and it's not, and the HP0 is not. So I don't know. I don't have many examples of computed first Poisson homology of associated varieties, associated schemes of vertex algebras. But this one is an interesting beast because we know that this is 0, for example, for classically free vertex algebras. So this is 0 if and only if GERV, which is A, is the arc space of its A0 part, which the arc space of RV. This always is a quotient of that, and we say that these things are isomorphic if the vertex algebra is classically free. So this guarantees that this space is 0. What happens if they're not? So if you followed the theorem, the proof of the theorem today, the same proof gives you for free that the dimension of H1 of K dot is finite if and only if the ideal from the arc space of RV to GERV is finitely generated. As a differential algebra, as a differential idea. So unfortunately, it's very hard to prove this for any vertex algebra. So for the Ising model, for the Virasoro Ising model, which is the easiest example of something where this guy is non-zero and is finitely generated, I only know how to do this with computers. I think Andrew Linshaw and Bai-Ling Song have examples now of algebras that have this ideal being finitely generated as a differential algebra. The problem is that it's very hard to come up with simple, nice vertex algebras with this property. So for example, I don't know it for the minimal model. We suspect that it's true for every Virasoro minimal model. So what we know is that if you take the Hamiltonian reduction of SL2 hat at level K is equal to -2 plus P over Q, where P and Q are coprime. And let's say 2 is bigger or equal than P, which is less than Q. If you take the Hamiltonian reduction of that, you're going to get the Virasoro vertex algebra a particular central charge. This thing is classically free. If and only if P is equal to 2. So in those cases, those Virasoro modules will have this vanishing. But if P is bigger than 2, we only know for P is equal to 3, Q is equal to 4, that ideal is finitely generated. So we don't know any other example, even among the Virasoro guys, that this ideal is finitely generated. So we don't even know how to prove that the Causal homology is finite dimensional, even though it's expected that it's 0. Sorry? On this? Oh no, so this is 0 if and only if this happens. So the dimension of this space is 0. Oh no, I'm sorry, yeah, so this is 0 if and only if. Yeah, so this thing here is 0 if and only if this happens. No, this I have no clue. I'm going to discuss this now in the next half hour, the last piece, the other limit that we haven't taken so far. So far what I've told you is a variation of a very trivial thing, which is if you take Causal homology, it's filtered by this taking order of poles of functions, and the Lie filtration on the vertex algebra, it looks like a PBW filtration. And if you take the associated gradient, you find the Poisson homology of RV and the Causal homology of GERV. And we found some conditions on these two algebras so that the Causal homology is finite dimension. So in particular, we've seen the theory that Anne has been describing to us of how the relation between the singular support of V with the arc space of the associated scheme appears in the theory of chiral homology. So now I want to actually see the Jou algebra and not just RV. So that's a different limit, and for this I'll need notes. And this is already here. When I take the actual differential without passing to the associated graded, there are components of this form. And I need to deal with that. And you see, this phenomena can only happen in chiral homology bigger or equal than 1 because there's nothing here in degree 0. So I couldn't have seen this before, this phenomenon. But at least let's start with this, with what happens if I take the full differential instead of just the top, the associated graded. And this leads to the following description of the Jou algebra. I'm not sure if Jethro has done this already in his lectures. I had to miss the last one. But stop me if you describe the Jou algebra as a quotient by... Okay, so probably I'll say the same that Jethro did. Probably it's going to be faster even. But on a vertex algebra, so this is a nice little game. If you give me any function f, let's say just a Lorentz series, like this, you can define a bilinear operation. Let's call it the f product. And then you ask when, if you kill the ideal generated by derivatives with respect to the f product, so you define this as zf. So the question is, the broad question here is, when is this guy, this quotient zf, an associative unital algebra with the f product? So you see, we already know one example immediately, which is if the function f is 1 over t, then zf is RV. So that's one example of a function that this works. Okay, so if I take the normally ordered product for the multiplication and I divide by everything that is a derivative, then this algebra happens to be associative and unital, and it's even commutative in that case. So now there's another example, which is when f of t is some constant times e to the ct divided by e to the ct minus 1. I mean, expand in power series of t this thing. And this zf is the Jou algebra of V. Well, not exactly. So this is the Jou algebra of V, at least when V is conformal. This is a theorem of Huang. And hopefully I'll get to say some words about what's the isomorphism between this and the Jou algebra, the usual way of describing the Jou algebra. But this is just simple. It's the quotient by this f product gives you an associative algebra. And these are the only two quotients, essentially. And there's some very mild rules that you're going to find for such that this thing is associative. But the beauty of this is that this comes naturally if you analyze elliptic functions. So if you want to answer this question as I posed it here, then you'll say, well, let's see. The first thing I need to check is whether or not this ideal is a two-sided ideal for the f product. This is going to give you a condition on f. What is that condition? The condition is that the derivative of f of t times the kth derivative of f of t is in the linear span, is in the C-span of the derivatives of f. The derivative of f of t, the second derivative of f of t, and so forth. And if you ask the question, well, when is it associative? Then you're going to find another condition that is that f of t times the kth derivative of f of minus t is in the C-span the same things. And if further you ask that it's unital with respect to the product, and you want the unit to be, of course, the image of the vacuum the vacuum element here, then you're going to find another condition that is that f has a pole of order 1 and it's the unique and it's a residue 1. So that f of t is of the form 1 over t plus something. And you see the Weierstrass zeta function wants to satisfy this. So the Weierstrass zeta function of t tau, this guy has, as a Taylor expansion close to t is equal to 0, remember it was 1 over t minus the sum k bigger or equal than 1 g2k plus 2 t to the 2k plus 1. This guy really wants to satisfy all of these conditions. It satisfies this on the nose, so this is a good. And if you take the derivative of the Weierstrass function, that's the Weierstrass p function, times any derivative of the Weierstrass function, that's some derivative of the Weierstrass p function, then that thing is a linear combination of derivative of the zeta function, which are just derivatives of the Weierstrass p function. The only problem is that the constants might appear. So constants are not here. Constants are not here. So the Weierstrass z function does not give us an example of an associative algebra, but still the quotient of v divided by v z v appears, I'm sorry, by v pv, which is the same thing as v divided by v tv with the Weierstrass zeta product. This quotient appears naturally in the theory of chiral homology. We already know that chiral homology, the honest chiral homology in degree 0, we have an explicit description for it. Remember that chiral homology in degree 0, h chiral degree 0 of v, was the quotient of v divided by, well, the 0th product of v. But then the other one is that, is the residue at t of the Weierstrass p function, a of tb, which is this. So this, that wants to be like the Jou algebra, well, it really wants to be like a Jou algebra, and this gives us, this appears in chiral homology in degree 0. So now, another interesting observation here is that if you grab that Weierstrass p function, that Weierstrass t function, z function, I'm sorry. I'm going to get this wrong, but I'm going to expand this thing in yeah, so I would want to give you an expansion of this function in terms of well, the first thing is this. Remember that this guy was periodic with respect to that change. It's not periodic with respect to tau. Not with respect to adding tau. But with respect to t plus 1 is. So I can expand in Fourier series in a series of the form e to the 2 pi I t. And also, I would want to take q. This is the first time that we are going to use this q to be e to the 2 pi I tau. And the expansion of this in those two variables, e to the 2 pi I t. So I'm going to take, no, I'm going to take explicitly this e to the 2 pi I t that I know that the Fourier series exists because this guy is periodic. Then that expansion is like this. Now I'm going to take q. Well, this looks like 2 pi I, and probably I'll get this wrong. 2 pi I t. This part is the only part that matters. 2 pi I t minus 1 plus a sum when n is bigger or equal than 1 of q to the n. Yeah, so here, I'm not sure what it is, but the point is that it's a multiple of q. So here I think is e to the 2 pi I n t minus e to the minus 2 pi I n t. Take this, probably this is wrong, but the point is that what is absolutely true is that whatever is here is of the order of q. In particular, it vanishes at q goes to 0. This is 0. This is almost true. And here was a discrepancy of something that Jethro noticed that last time. I was always using the Weierstrass z function, but to make this expansion correct, I need to correct this Weierstrass z function in such a way that I start here at k is equal to 0. That's going to add a term g2 here, and this g2 is going to make it such that when zeta of t plus tau, this is equal to zeta of t tau minus 2 pi I, or probably minus pi I, instead of the g2 that I had last time. So that was the discrepancy. So I'm just deforming this function by adding a linear term, and this becomes true. But now you see something beautiful. The limit of this thing as q goes to 0 is the function that actually we need to kill to get the Joux algebra. So this function here has two limits. This is defined on a lattice that was given to me by these two periods. I've chosen a specific basis for that lattice to be 1 and tau, but I can just take any lattice and I will have a zeta function. If I take the limit as one of the periods goes to infinity, I get the function that I need to quotient by Joux to get Joux algebra. And if I take the limit as the other one goes to infinity, I get 1 over t, which is the function that I quotient to get Joux C2 algebra. So that I think is a beautiful theorem, and we don't understand. It's a very simple thing, but we don't have an understanding as to why. So we don't have a deeper understanding of that statement. But you see immediately that if I take a limit as q goes to 0, I see the Joux algebra when I look at the quotient of v by v, z, p, v. Okay? So that's a very simple lemma. The limit as q goes to 0 of v divided by the residue at t of Weierstrass p function of t, a of t, p, this is the Joux algebra. So as I take the fiber of chiral homology at the nodal curve where q is equal to 0, then I expect to get a quotient of the Joux algebra because this guy here was in chiral homology. It's part of the differential. So what I need to kill left is a quotient of Joux of v divided by guys of the form a0b. But actually this goes to the commutator of Joux. So this here is the same in Joux is Joux of v divided by commutators, Joux of v. So we've proven something very simple, that if you grab the chiral homology complex, don't take the associated graded, remember the whole thing, but take the funny limit as q goes to 0. In that fiber, you get the 0th Hochschild homology of the Joux algebra. And this is therefore the limit as q goes to 0 of chiral homology xv. And this happens for any vertex algebra. This doesn't require any finiteness condition or rationality nor anything. We haven't used any. Okay, so I want to prove the same statement for first Chiral homology, and that's non-trivial. This requires some nasty-looking formulas because, I mean, I've avoided the whole complication of this by taking associated graded, and certainly I don't remember the formulas, so I took notes of that when I don't take the associated graded. So when I don't take the associated graded, oh, come on, wake up. Face recognition never works. Apparently, okay, there we go. So, okay. So what I'm after is the following theorem. This is our theorem that is a few years old now with Jethro and myself, which says that, why did I miss the formulas? These are the formulas I want. So the theorem says that the limit of the Chiral homology in degree 1 of an elliptic curve, well, the situation that we are now, as q goes to 0, is isomorphic to Poisson homology in degree 1 of the U algebra if V is classically free. It would be much, much nicer to have this theorem without this condition because that would imply only a condition on the Poisson homology of RV to get finite dimensionality, for example. But as of now, we do not know how to get rid of this condition. So how does that go? Well, what I'll do is, well, let me tell you what are all these differentials. We'll need some nasty looking ones. So remember I had this function that was p z. And I want to take a differential of that, tensor A, tensor B, tensor C, without taking associated graded. So I'm going to write it instead of like telling you how the computation goes. But this goes like this. It's a horrible thing. So this is going to be minus 1 to the j. No, this is not going to. It's as horrible that this is not going to fit here. So let's take a full board. So the differential of this function p z a tensor b tensor c is a sum of minus 1 to the j over j plus 1 factorial L minus 1 to the j applied to A tensor B j plus 1. Oh no. I'm doing this wrong. I'm reading this wrong. Okay, that's why I never use notes. So this is L minus 1 to the j of the product of x to the j plus 1 p of x b tensor c plus, oh, here's the p function. So it's minus p tensor that plus, again, p tensor, the sum of 1 over j plus 1 factorial, L minus 1 to the j, tensor A of A, tensor b x j plus 1 p of x c. Come on. Okay, C, that's correct. Let me just take the same sum here. This is L minus 1 to the j times b tensor A x j plus 1 p of x. This looks horrible, but it has some beautiful limits. C. And then here's the trick. 2 pi I square Q times d by dq of this thing, which is AZB tensor C minus A tensor BZC minus B tensor AZC. And this goes with the function 1. Okay, so let's analyze this formula here. I mean, remember this, how did we compute this full differential? We grabbed this function and we took Taylor expansions of these functions along each one of the singularities. For example, I could look at the singularity where this guy here had a 1 over x minus y. So as x goes to y, I pick up a singularity, and then I need to expand this function, and then I had this other p function. So previously, I only looked at the singular part, but now I need to, when I take the Laurent expansion of this product, I pick up the derivatives of these p functions, and that's what appeared here. So when I write here these products, remember, this meant a of x times this function applied to b, take the residue at x. So if you see here, this sum, all of these sums are over j bigger or equal than 0, j bigger or equal than 0. So this starts here with a pole of order 1, because p is 1 over x squared. This starts at least with x. So this product starts with 1 over x, and then the next term is already regular. So the first term in this product is a times b, tensor c. And the first term in this product is b times c, tensor a. So these are the things that already appeared when I took the associated graded. So if you look at the first term of these two sums, this was the horizontal differential in that diagram that we had in this board. Is the p function times this, which is very simple, is just a times b applied to c, and b times c applied to, and then a tensor that. Okay. Now this piece here is new. This piece here is new, and it comes with the function 1, and to get this piece is a long computation. So you take all the Taylor expansion, and then you use an identity that tells you how the Weierstrass zeta function behaves with respect to derivatives with respect to q. So this is a non-trivial, it's a long computation, but it's a straightforward computation, but you need to recognize this expression in the form of this expansion. The point is that as q goes to 0, this thing disappears. So the moral of the story, with this I want to finish, is that when we've taken the associated graded of the Causal homology complex with respect to the Lie filtration, we found the arc space and we have found conditions on RV. As I take q goes to 0, what happens is the following. As q goes to 0, some of the terms in these differentials disappear because I see explicitly expressions of this form, q d by dq. And since some of the terms explicitly disappear, the complex splits. So what are the components? It splits up a subcomplex that I want to slightly describe. So this subcomplex is as follows. So again, we have in degree 0, degree 1, and degree 2. And here we had functions of the form pp, pz, pz, and 1. And here we had functions p and 1. And here we only had functions 1. So if I get this correctly, what we can do is pick up this guy's piece from here. So I'm going to take this p from here, this piece from here, this pp from here, and the zeta from here. And those smart components that I said define a subcomplex B that I'm not going to have time to describe, so it doesn't matter. But inside of the full chiral complex. So this is a different story. Before I took an associated graded and I had a subcomplex which was the top row, this is a subcomplex that appears because some of the differentials become 0 at that Q. So for example, the differential of this guy here goes to 0, so I can take this guy and take this guy in the same component. So because of that happens, I have a subcomplex without taking associated graded here. And the quotient I call Q. Again, one writes down the long exact sequence for these complexes now. They are slightly different than the previous one, but they use the full differential. And the point is that you find that the chiral homology in degree 1 fits between the Poisson homology of RV in degree 1. This didn't change before. Oh, sorry. The Causal homology in degree 1 of A. This didn't change as before, but this we computed again by taking a filtration. And the Causal homology on degree 1 of Ju. The reason why this appears before we took Poisson homology in degree 1 of RV, when we passed to the associated graded. So the complex that computes this Causal homology is filtered. If you take the associated graded with respect to that complex, you're going to get this. So it's not surprising that you find this. This, again, you have a complex that if you take an associated graded, you find again this guy. And this is our condition of being classically free. This is 0 if V is classically free. And therefore, this guy becomes isomorphic to that in that limit. Okay, so that's the idea of that theorem. Some questions are, can we get rid of this? Is this complex that has vanishing homology without it being classically free? We do not know. Actually, I don't even know if we even have a conjecture about that. There's so many things that I haven't talked about. For example, if you take Jou's theory, it's not about coinvariance. It's about traces of modules, and I've never mentioned, which are the duals of this. And the complication there is to prove convergence. There's something similar for chiral homology in degree 1. If you look at the duals, you're going to get series that converge exactly in the same way as Jou, and the complication there is to prove convergence. I decided not to talk about that because we don't have a single example. We can construct these series out of self-extensions of modules which don't really exist for interesting simple vertex algebras. So we expect that that's going to give us something for C2 cofinite non-rational vertex algebras, but we don't know a single example where self-extensions exist. So perhaps this doesn't even exist. There might not be an example of a self-extension of simple modules for C2 cofinite simple algebras that are non-rational. This is an open question as far as I know. But if you give me an example, I can produce classes in chiral homology. Okay, so I'll stop here. So this is the limit as Q goes to 0. What?
Okay. But does connection extends to the?
Oh, that's it. Yes. So, yeah, I didn't say this, but it's the same way. So, the connection. Remember what was the connection in degree 0? If you have an element A, then I wanted to define how d by d tau acts on an element in your vertex algebra, and I defined it to be like this. You take the conformal vector, you take a function that is not well defined on the elliptic curve. You take the conformal vector, you take A, and you take the differential of that. So this is the residue, Z of X, L of X, applied to A. Do the same thing. So now in the next degree, you're going to have A tensor B in degree 1. And I want to tell you how d by d tau acts here. And you're going to do exactly the same thing. We're going to add one extra guy. So this is going to be in degree 2. So this is going to have omega A B. And we're going to multiply by a function that is not allowed. So here I am allowing functions that have a residue at x is equal to y, x is equal to 0, or y is equal to 0. So here, what you do is you put x. That's correct. So you take this and take d of that. So this is not a well-defined function. So if I had that extra combination, x minus y minus z of x plus z of y, this was well-defined, but this guy is not well-defined. But I take d of that, and this is, again, a residue. This is the connection. So you see the same singularities than for the degree 0 case. So the bundle extends, and this connection has a regular singularity at q is equal to 0, both in degree 0 and in degree 1. And of course, this extends for every degree. So I think, so for general curves, it would be very nice to have something like Damellini, Gibney, and Tarasca's papers relating higher chiral homology and factorization of higher chiral homology. As far as I know, this is not worked out. But it seems to me that that theory should be extended to this setting, not hard.
So if the factorization holds, then theorem is.
I'm sorry, if the factorization holds, then?
Theorem is obvious for rational.
I'm not following. So you're saying that if the factorization holds, then this theorem would follow for rational vertex algebras? Why? How do you get rid of the classical freeness?
My question.
No. So, so we do not know how to get rid of classical freeness. So you see, for rational vertex algebras, so what is an easy corollary of this theorem is the following. If you give me a rational vertex algebra that is classically free, then its chiral homology vanishes in degree 1. Because if you're a rational algebra, then this vanishes because U is semi-simple. So the limit as Q goes to 0 vanishes because of this classical freeness. And now we know that we have this connection, and then with this connection, we can extend it to inside. So, but we do not know how to prove for rational vertex algebras that the nodal curve limit has vanishing chiral homology, because we cannot get rid of this condition of classical freeness. So that's why we know how to prove chiral homology vanishes for the minimal models of type 2 something. But I don't know how to do this for all minimal models. So I've seen talks of Dennis Gatesbury where he relaxes a little bit the condition of what chiral homology is. So he doesn't really define chiral homology in the usual way as Beilinson and Drimfeld, and then he proves vanishing of that chiral homology for all minimal models, and actually probably for all rational W algebras. I think it's concentrated in minimal models, but so it might be a subtlety of the actual definition of chiral homology as in Beilinson and Drimfeld, which I'm following, versus having a better suited chiral homology definition. Well, this is in algebraic geometry. So this chiral homology a la Beilinson and Drimfeld is global sections on the run space. And yeah, so perhaps I can tell you in a different way, because it's more involved. His definition is only adapted for the category of affine vertex algebra, so representations of the affine vertex algebra. And then he takes coinvariance with respect to only things that come from the affine vertex algebra itself. So it's not really the same as when it's contract. I don't see how. You mean this isomorphism here? Yeah, no, I don't see how. I I don't see how, because so you'll have to prove. So let's say that you take this for the normal elliptic curve. Then you'll have to compute chiral H1 for P1 with coefficients in a bunch of modules. And yes, so if you have control over that, then I'm happy. So I have a student working on related questions, but. No, analyzing, no. Besides factorization, you need to understand what is chiral H1 for P1 with coefficients in modules supported at points. So you need, so to get to Muyuki's, I think you need to prove what is chiral H1 for modules, then use factorization, and then try to get rid of classical freeness. I don't see, so that's a long program.
Cannot show that the H1 defines a vector bundle.
Yes, so this we've shown, that H1 defines a vector bundle on the moduli space. Well, if this space, if this homology is finite dimensional, it might be 0 in the classical free, but if it's finite dimensional, then we already know that chiral homology is finite dimensional. So this is a finite rank bundle. You have a connection. This extends to the boundary, but we do not, yeah.
So if it's 0 for the northern curve, then it's 0.
Yes, that's correct. So that's the way we've proven that chiral homology is 0 for the minimal models of type 2 something. By saying, well, if it's 0 for the northern curve, since we have a bundle with a connection, then it's 0 everywhere.
So then it proves the vanishing H1.
Sorry?
So it proves the vanishing H1.
This proves it in the case where you have this classical freeness, because we can only prove that it's 0 on the northern curve when you have classical freeness.
Already at the northern curve, there's possibly a contribution coming from non-classically free.
Right. So for the Ising model, we can prove that this homology is of dimension less or equal than 1. It's supposed to be 0, but we know that it's of dimension less or equal than 1.
Even on the northern curve.
Yeah, so this limit is, so it would be nice. So I think this, Damilinis, Gibney and Tarascas, they can actually define, the same way that I did, but they can define this. So instead of giving you a limit of this, they can define this object already on the northern curve by taking a resolution of the northern curve and putting 2 different modules on the preimages of the nodes. So if you can compute those, perhaps you can get rid of this classical freeness condition. But the problem that I see there is that for higher, something I mentioned in the second lecture, for higher genus, the Riemann-Roch theorem tells me that I can't really find enough vector fields that would play the role of the Weierstrass-P function here for the elliptic curve. So I don't even have finite dimensionality. So in their case, they use both that V is rational and that V is C2 cofinite to find finite dimensionality of these vector bundles. We don't need C2 cofinites. We only need quotient by Poisson brackets. And we don't need rationality for, but we have this Weierstrass-P function that allows us to do so. So I don't know, I think the complication in their work to extend for higher chiral homology is going to come to prove finiteness without using rationality and finite dimensionality. Yeah, so I don't have an easy way of proving that higher genus chiral homology is finite dimensional if I know that the Poisson homology of RV is finite dimensional. That I think is a nice question, and perhaps it's not hard.
But if you would propose to use their method to remove hypotheses of classically free, you don't need to go to higher genus.
If I'm sorry?
If, as you said, perhaps their method could give proof of the theorem without the hypothesis of classically free, you don't have to invoke higher genus.
Oh, no, I agree. But then, so there's a trade-off. You don't invoke higher genus, but then now you need to look at module insertions. And module insertions come up with similar questions, with similar problems. When you're looking at sections with poles with prescribed poles at each one of the insertions, it's a sort of like the same kind of game with Riemann-Roch for higher genus.